algebraic combinatorics. I'll give you guys more information as soon as I have it. Soon. A week or two, I'm hoping. June 11th to the 22nd. Yeah.
That'd be cool if you could present on like the projects.
Yeah, absolutely. Absolutely. Okay, so this class might be a little bit short. We'll see. I always think it's going to be short, but I always go slower than I think I'm going to go, which I'm happy with. But so I want to do two things. The first thing is just talk about some generalities about Hopf algebras that are useful. And then I want to talk about graded Hopf algebras. So we talked about graded algebras, and now I'm going to talk about graded Hopf algebras. And I think the main point of the class today is that if you have a graded Bialgebra, then the antipode comes for free. Okay? I told you that often you have a Bialgebra and you know. Oh crap! Give me a second. This thing just ran out of battery. Yes, I was saying that sometimes the antipode comes for free, and I'm going to make that precise now by proving that if you're graded, then you have an antipode. Okay? Give me a second. Okay, that was fast. So, but let's first start with some generalities about Hopf algebras that are useful. So, some other properties and constructions. Properties and constructions. So, one property is the following. Let's say that you have two Hopf algebras, let's say H and L. Okay. So one thing we haven't talked about, I define Hopf algebras, but as in all of these things, you very quickly want to talk about mapping one to another one. Okay? So you can ask about maps from one Hopf algebra to another one. And a lemma that's very useful is this one, that if you have a function from H to L, which is a Bialgebra map, okay, meaning that it preserves the algebra structure and the co-algebra structure, so it preserves multiplication, unit, co-multiplication, and co-unit, then it comes for free that is going to respect the antipode also. So this is also a Hopf algebra map. A Hopf algebra homomorphism. In other words, aside from being a Bialgebra map, it also preserves the antipode, meaning that if you, let's see, what do I want to say here? If you take something in H, and then you apply the antipode of H, and you apply the function, you're going to get the same thing as if you first apply the function, and then you apply the antipode of L. Okay? So that's a very useful property. And if you want to see the proof, you can see it in the book. Sweetler. Lemma 404. Okay? So that's a nice tool to show that you have Hopf algebra maps. given again that we're going to talk about maps, we very quickly want to start talking about, you know, what are ideals, kernels, etc., sub-Hopf algebras, etc. And so let's talk about that, ideals and quotients. So if you have a Bialgebra B, then what does it mean to be an ideal in a Bialgebra? Well, that should mean that you're an ideal both in the classical sense and in the sense, in the co-algebra sense. So say that a subset is a bi-ideal if it is both a two-sided ideal and a two-sided co-ideal. Okay? And in that case, we can consider the quotient B mod I, right? And that's going to be a Bialgebra, and the reason for that is simple, because, you know, I is an ideal, which means that B mod I is an algebra. I is a co-ideal, which means that B mod I is a co-algebra, and the algebra and the co-algebra structures were compatible in B, and so for free they're going to be compatible in B mod I. And so we're going to call this the quotient Bialgebra. Okay, so that's how you take quotients. And naturally, you can imagine that the first isomorphism theorem is going to hold here also. Okay. So the image of a map is equal to the codomain modulo the kernel. They're isomorphic as Bialgebras. Okay. All right. So that's for Bialgebras. Now, let's say that we want a Hopf algebra. We have a Hopf algebra. And we want to define what it means to be an ideal in that context. So we take some subset of H, and we're going to say that this is a Hopf ideal. If what? What do you guys think? What should we require in order to be a Hopf ideal?
That it's a bi-ideal. And also that the antipode of the ideal is the same as the ideal.
So it should be a bi-ideal, right? Because this is supposed to be stronger than this, but the antipode needs to come into play. And so how are the antipode and I supposed to be related? Well, I'll write the condition in a second, but let's think about what we need. So we have the antipode from H to H, right? And we want to have an antipode on H mod I. Okay? So we need, I mean, one thing we can do for sure is I mean, how do we define this map? Well, we certainly have a map from H to H mod I, which is just, you know, taking the antipode and then modding out by I. And when does that descend to a map? Let's call it maybe S prime from H mod I to H mod I. And that's going to work as long as I is in the kernel of this map. So this is going to work if S of I is, so if I is in the kernel of this map, which means that it gets mapped to 0 here, which means that it gets mapped to I here. Okay. So the condition, therefore, should be that S of I should be inside I. Okay. Which is exactly what Alejandro was saying. And I claim that that's all you need. If you have this, then, well, we have a quotient Bialgebra, and this is going to be our antipode for that, and it's going to be compatible because all of that is going to be inherited from the original Hopf algebra. So again, we say, so in that case, H mod I is a Hopf algebra, the quotient Hopf algebra. And as before, we have first isomorphism theorem. Okay. By the way, I should say with all of this that the first isomorphism theorem is one of several, and you can go through the work of taking the other isomorphism theorems and extending them to this. This is the one we keep using all the time, so that's why I keep talking about this one, but it doesn't mean the other ones are not true. Okay. Okay, so these are some kind of generalities, ideals, quotients, etc. And naturally, we might also want to talk about duals. Right? So if you have a Hopf algebra, and now let me say, it comes with, I don't know what order I wrote it down here. Multiplication, unit, co-multiplication, and co-unit. Okay. So if this is a Hopf algebra, well, actually, I'm missing something, right? Because so far this defines a Bialgebra, and if you want a Hopf algebra, you need to have an antipode also. Okay. So what is the dual going to be? Well, we take the dual vector space. For a multiplication, we use the dual of co-multiplication. For unit, we use the dual of the co-unit, etc. What should we use for the antipode? So the antipode goes from here to here, from H to H, and we need some map from H star to H star. So we can't use the same thing because these are different worlds, H and H star. But given a map from H to H, there's a natural map, which is the dual map of this one, which goes from this star to this star. Okay? And so that's what we need to put here. Okay? So this is also a Hopf algebra. This is the dual Hopf algebra under some conditions. So what do I need? Finite dimension. And that's because of that issue that the dual of a coalgebra is an algebra, but the dual of an algebra is not necessarily a coalgebra. Okay. But in finite dimensional land, there's no problems. Okay? So this is all stuff you can check, nothing terribly complicated there. But there are some generalities that I wanted to record to make sure that we have them on paper. And you'll realize that in the homework, I'm asking you to check some of these things, right? So for example, I ask you to check that something is a Hopf ideal so that you can mod out by it. And so This is what I mean by that. Okay. So the next thing I want to say. So that was the first part of the class today. Very kind of general. I didn't go into too many details. And for the second part, I want to spend the rest of the hour talking about graded Hopf algebras. Okay. And someone had one of the hidden motivations here is that often the antipode of a Hopf algebra comes for free. So maybe, well, I wrote the subtitle before the title of this section, but the title of this section is Graded Hopf Algebras. But actually, I should say that this is not the only subtitle. So one nice thing about graded Hopf algebras is that the antipode comes from free. But we will see throughout the rest of the semester that actually most of the algebras that we care about are graded. And that's because things in combinatorics often tend to be graded. Okay. We'll see. You'll see more precisely what I mean by that. But before we say that, well, I need to actually say what it means to be graded. So let me say that we already talked about what it means to be a graded algebra. Right? So now let's talk about what it means to be a graded bialgebra. Bialgebra B is graded if I have a decomposition of B as a direct sum for n greater than or equal to 0 of Bn. Okay. And again, we think of the elements of Bn as being things of degree n. Okay. And then we're saying that every element of the bialgebra can be written uniquely as something of degree 0 plus something of degree 1 plus something of degree 2, etc. Some finite sum like that. But we need some properties such that we need some properties. Okay? And one property we already talked about, which is that if you multiply things that are homogeneous of degree I and things that are homogeneous of degree j, you should get things that are homogeneous of degree I plus j. Okay? This should be true for all natural numbers I and j. Okay, that's just the graded part. Now, what about the co-grade? Sorry, that's just the algebra part. What about the co-algebra part? So the input is a single thing. And so this should talk about what happens when you apply things that are of degree n. And what do you think should happen? It should be things, it should be a sum of things of the form something of degree I, something of degree j, where I plus j is equal to n. So the degree gets distributed among the two components. This should be true for all natural numbers n. And we are also going to demand that the co-unit kills everything of positive degree. So the things of degree 0 don't have to be killed, but everything of degree higher has to be killed. Okay. So that's graded Bialgebra. And we say that a graded Bialgebra is connected if the things of degree 0 are just a copy of the field. Okay. It could, I mean, in principle, B0 is some vector space over K. But we're saying B is connected if that vector space is just one copy of K. It's just a vector space of one generator. Okay. Does what come from topology? The word connected?
Yeah, I mean, I don't want to bring it up. That's just like narrow.
Maybe let me say that it doesn't only come from topology. This we'll see in a lot of examples that we want this and we have this.
I mean, I know that when you work with what's it called? Simplicial homology, the first technology of what the connected components of the space are. But I don't see how it's
Let's take that to the forum. So because I told you, and it is important to remember that a lot of these Hopf algebras come from cohomology rings of spaces. And so, if the space is connected, does that have to do with this word, this use of the word connected? I think that's what your question is. So, will you put that on the forum? Thank you. Okay. Let's talk about some examples. Examples of Hopf algebras that are graded. So maybe the first. Oh, a graded Hopf algebra is a Hopf algebra that is graded as a Bialgebra. So that's anticipating my next. I'm going to show some examples, but my next theorem is that any graded Bialgebra is a Hopf algebra. It has an antipode. And therefore, I don't really need to insert any more adjectives. The next step comes for free. I should say a graded connected Bialgebra is a Hopf algebra. Examples. First example. What's the first example? Polynomials in one variable. If we're not too ambitious, polynomials in one variable. So let's check the conditions. Okay. So here, hi is the multiples of x to the I. Yep. So let's check the conditions. Bi bj is a subset of bi plus j. Well, that's true because x to the I, x to the j is equal to x to the I plus j. Second condition, the coproduct of x to the n. What is that? We saw that this is equal to n choose I, x to the I tensor x to the j, where I plus j is equal to n. Okay? And so this lives here as it's supposed to. And finally, we also know that here the co-unit of x to the n is 1 if n is equal to 0 and 0 otherwise. Okay. And so this holds it well as well. Okay. So that's an example of a graded bialgebra. And you'll notice that it is connected, right? Because H0 is just the multiples of 1, and this is just K. Okay. So that's the first simple example of a graded bialgebra. Let's do a more interesting example. Let's say that we consider the bialgebra of isomorphism classes of finite graphs. Okay? So what should what sub h sub n be? In other words, given a graph, what degree should I give it? There's not that many options, right? Either you grade by vertices, or you grade by number of vertices or by number of edges, or it could be trickier, but hopefully it's either vertices or edges. Okay, so let's figure out what we need. We'll just say that this is the isomorphism classes of finite graphs. With n fill in the blank. Okay, and we'll see if it's vertices or if it's edges, or if we have to get trickier than that. So let's check the conditions. Here you can kind of do it pictorially. So you have a graph that has I somethings, either vertices or edges. So here's my graph, and we're going to multiply it by, so here's my graph, and it has I fill in the blanks. We multiply it by some other graph, which has j fill in the blanks, and I get the disjoint union, right? That's how you multiply in this algebra. And I need to have I plus j fill in the blanks. So can we decide if it's vertices or edges? Well, so far, either for vertices or for edges, that works, right? If this has I vertices and j vertices, this has I plus j vertices. If this has I edges and j edges, this has I plus j edges. So far, we haven't had to make up our mind. Okay. Now let's apply the coproduct to a particular graph. Okay. So here's my graph. Let's say that it has n fill in the blanks. So what is this? Remember, this is the sum over subsets of the vertices of something tensor something. And the something are, let me draw it like this. Let's say that this is my set S. I meant to draw this. So I restrict the graph to this set of vertices, and then I restrict to the remaining vertices. Okay. So this has I somethings, and this is j somethings. So is it true that I plus j is equal to n? Not with edges, right? Because if this graph has I edges and this graph has j edges, then G, it certainly has those, these I edges plus these j edges, but there's all these cross edges between S and B minus S that you lost when you split the graph in two. Okay? And so that means that we shall not put edges here because that would not be a proper grading for this thing. But if we do it with vertices, this works, right? If this has I vertices and this has j vertices, then this has I plus j vertices. Okay. So vertices are fine. Okay. And what about the last condition? We just discussed this during office hours earlier, and that the only possible co-unit for this thing is that epsilon needs to take if the graph is empty to 1, and if the graph is not empty to 0. Okay. But saying that the graph is empty, I mean, really what I mean by this is that it's the graph with no vertices and no edges. If G has no vertices, no edges, and 0 otherwise. Okay? So that means that this is graded, and is this connected? What is H0? H0 is, the span of the isomorphism classes of finite graphs with 0 vertices, and there's not that many graphs with 0 vertices, right? There's only one, which is the one that has no vertices and no edges. So this is K. I mean, it's the span of the trivial graph, and therefore it is a copy of K. So this is a connected, graded Bialgebra. Okay. Okay, third example. Linear combinations of permutations of the numbers from 1 up to n. Okay. And remember that the products are cutting, the product and coproduct are shuffling and cutting in some order. So the product is shuffling. Well, before that, so what is Hn? What should we call the degree of a permutation? The most obvious thing is the number of elements, right? So let's see if this is a grading, permutations of n. And now if you take pi 1 and pi 2, so these are a permutation of n1 and a permutation of n2. And remember that when we multiply them, we just shuffle in every possible way. Okay? So this is the sum of the shuffles of pi 1 and pi 2. And therefore, if you have I cards here and j cards here, you have I plus j cards here. The coproduct of a permutation was taking our deck of cards and cutting it in two in all possible ways. Sum over the cuts of permutation of the top. I'm being very loose with my notation here, as you can see. We cut and we put the top and the bottom as permutations, and if this has n cards, then the total number of cards here is also n. again, I think I didn't mention this, but the co-unit again has to be 1 if pi is trivial, is the only permutation of the empty set, and 0 otherwise. Okay?
Let's just do the day. When we take delta there, we include the sort of trivial cut, right? Where I've got a deck of cards and I take no cards in my right hand and all in my left.
Mm-hmm. Yep. And H0 is k of the permutations of the empty set, which again, there's only one permutation, which is the empty permutation, and its linear combinations are a copy of k. All right. So that gives me another example. Okay. Maybe with all these examples, we should do a non-example also, just so that we see that there are some things that are not great. Not really. I mean, let me give you an example of. So there's tricks that you can do. Let me give you an example of something that would be graded and not connected. Except that I'm doing this off the top of my head, so I'll let you fill in the details. But you can imagine, for example, that H consists of, I don't know, permutations of n, where each card is either face up or face down. Or each card is either blue or red, let's say. Okay? And then you still shuffle and you still cut, but now you kind of have two different, each permutation can kind of be face up or face down. And so maybe you can arrange it so that actually you have an empty permutation that's blue and an empty permutation that's red. Okay? And so I'm fairly sure that you can make this work and make it into a Hopf algebra where everything works, is graded, it's just not connected. Okay? Now let me show you something that is just not graded. So a non-example. So maybe let's call it non-example 1 instead of calling it example 4. Non-example 1, let's consider the isomorphism classes of intervals of posets, or finite posets with 0 and 1. Okay. So let's say that we wanted to grade this. So how would we grade it? We would have to decide for every interval, grade by something. Finite posets. Let me, instead of I keep saying finite posets with 0 and 1, let me just call them finite intervals because they have a bottom and a top, so they're intervals. Okay? So let me just call this interval. Isomorphism classes of finite intervals with n something. Okay, so the thing is that how do we multiply two posets? We take the direct product, right? And so maybe the most obvious grading would be to try to say finite intervals with n elements. But you will see that if this guy has I elements and this guy has j elements, the product has I times j elements, not I plus j elements. So that obvious grading doesn't work. Okay? So can you think of some other grading that might work? You could say, how tall is it? How tall is the poset? Okay? So what if you take something of height n? So the longest path from the size of the longest chain from the bottom to the top. So if P has height I and Q has height J, does the product have height I plus J? So if this has height I, this has height J, then this has height I plus J. Let me, okay. I'm getting a little bit nervous about whether this is a non-example or not. Let me say what a real example is. So some posets are graded. And graded means that they really have levels. Level 0, level 1, level 2, etc. Okay? And so a poset P is graded if for any x less than or equal to y, all maximal chains from x to y have the same length. Okay. Maximal means that it cannot be refined. Okay. So if I go from x to y, up one chain, and up another chain, if this chain has length 3 and this one has length 2, that must mean that this one is not maximal. I need to have somebody else here to refine it. Okay? So this is an example of something that is graded. And this is an example of something that is not graded. Okay? An alternative definition is that a graded poset has levels. This is level 0. This is level 1. This is level 2. This is level 3. And whenever an element covers another element, the change in level is exactly equal to 1. You cannot possibly do that here, because you cannot decide if this should be level 2 or level 3. Okay? So let me say example 4 slash, and I think this is not example 1. I think so too, but kind of stalling here while I while I think of whether this is. I'm not stalling because actually I need you guys to know this also. Graded posets, and this is a useful example. So isomorphism classes of graded finite posets. Okay, this is actually a connected graded Hopf algebra with height. Okay, and it is true. It's a lemma that if P has height I and Q has height J, then the product has height I plus J. That is true. What about coproduct? So I take delta of some interval. Okay, so this has height n. So this is equal to the sum of all the ways of doing this tensor this, right? And if this has height I and this is height j, then if we are graded, that means that this is at level 0, this is at level I, this is at level I plus j. Okay? And so I plus j is equal to m. If we're graded. Okay? But if we're not graded, this might not be true. Because maybe you have a path from here to here of length I, and a path from here to here of length j. But that doesn't mean that every path from here to here has length I plus j. Like here. So for example here, delta of this guy would include the term this tensor this. Right? And so this guy that we would like to put in level 3 would be, when we apply delta to something on level 3, we would get something of level 1 tensor something of level 1, which is not what we want. Okay? And so let me get rid of this question mark. Okay? This grading works if my finite posets are graded, but it doesn't work if they're not graded. Okay? And everything else is easy. Okay? So epsilon, also easy, and h0 also easy. Okay? So it works if you're graded, it doesn't work if you're not. Okay? So these are different examples of graded things. Okay? But I hope that these examples give you the idea that, I mean, as in the second half of the class, we're going to be doing a lot more examples of concrete combinatorial things, and the grading comes from the combinatorics, as you can see in these examples. So let me state a theorem, and this is a theorem due to Takeuchi in 71. It says that any graded connected Bialgebra has an antipode. Okay? But it's not just an existential theorem, but it actually constructs it. So let me tell you what it is. So if I define pi to be I minus u epsilon, okay? And this is one reason that I wanted to clarify in the last class that we're talking about two different identities here. So this is the identity map from H to H, and it's the identity under composition. And this is the one of the algebra. This is the identity of the algebra, and they're different from each other. And pi is going to measure the difference between them. So this goes from H to H. Then the formula for the antipode looks like this. We'll parse this. we'll parse this. It's some explicit formula. Okay. This is the antipode. Which turns H into a Hopf algebra. I hope you come to know and love this formula. It is very nice that it's very explicit. You know, given this very general setup, you're graded, you're connected, you would get this explicit formula for the antipode. Okay. Now, do you want to use it? Sure. Never? Oh, you don't even know what this means just yet. So let's think about what this means. It's not too bad, actually. You'll see it's not too bad. You know in this class everything looks much harder than it really is. You know that by now, right? Everything in Hopf Algebras, when you look at it, looks very complicated, but it's not that bad.
How did they do that?
I have an issue.
You have an issue?
Would that be n greater than or equal to 1?
No. So I'll tell you. So here we're using a convention. Yeah, it's a fair complaint because what does delta to the minus 1 mean and what does m to the minus 1 mean? And the conventions are, and also, I mean, well, maybe this is clear. What is m0 and delta 0? These are just the identity map. And that's fair. I mean, you compose a function 0 times. It should be the trivial function. In other words, I mean, you want this to be true, right? You want mi composed with mj to be mi plus j. And therefore, you should define m0 to be the identity of composition. Now, what should you define this to be? Well, actually, and what should you define this to be? So what you want to do is this and this. And with this convention, this formula is true. Okay. So I'm going to prove this. And actually the proof is not even too bad. But let's first think about what this actually is doing. So this is saying, okay, look at every possible value of n. Take the nth coproduct, the n minus first coproduct. Right? And so this gives you a bunch of n tensors. Then you apply pi to, so this is the nth tensor product, meaning you apply pi to each coordinate. And so all you're doing is applying this to each coordinate, and we'll see what this does. This is easier than it seems. And then you have your n coordinates, and you multiply them. Okay. And so it's like, you take your, we talked about how coproducts are kind of taking things apart, right? So you take your element, you take it apart into n pieces using the coproduct, then you apply this pi to each piece, and then you bring them back together. You multiply.
But that reminds me of the isomorphism problem. I mean, I being the identity minus 1. Is that way off?
I'm not sure what you're referring to, but the equation sounds a little bit like you're right. I mean, this should look a little bit like a geometric series to you, doesn't it? Something like that. And maybe that's kind of what you mean also. It's something like that.
Really an infinite sum?
That's another very good point. It better not be, right?
Yeah.
So how do we know that this is not an infinite sum? So actually, before we try to prove this, we should make some remarks about why this even has the possibility of making sense. And that's one thing we should check. So let's make some observations about this formula before we prove it. So first observation is that this better be 0 eventually. So how do we know that this thing is 0 eventually for n large enough so that this sum is not infinite? Let's say that we take S and we plug in something homogeneous of degree n. Okay. Well, let me not use n. Something homogeneous of degree d. Okay. So this guy lives in degree d. Okay. So how do I know that this sum is finite? Well, the thing is that if I take the n minus first coproduct, where does that live? If I take the n minus first coproduct of something of degree d, that needs to live in. Actually, let me just write this here. So if I take something of degree d and I apply the coproduct n times, then this needs to belong. I mean, this is going to be a big sum of things. hi1, tensor h I k I n, where I1 plus dot 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 plus in is equal to d, right? If I take something of degree d, then the degree has to be distributed among the tensor product. Okay? So what? So let's say, for example, that n is bigger than d. So then what happens? So if n is bigger than d, we have n numbers that add up to d. So we have more numbers than the thing we're trying to add up to, which means that one of them is 0. Okay, so I'm realizing I got carried away in my notes and I said what you said, but I'm realizing it's not right. So it is true that one of the, or at least maybe I'm misunderstanding what you're saying, but I know what I wrote and is wrong. What I said, okay, so that means that always one of these guys is 0. So in every term, sum ij is equal to 0, and then I said that we're done, okay, because then this is equal to 0. But we're not done because, so what if that means that some of these things are of degree 0. What's the big deal? We multiply them. That doesn't mean that the answer. I mean, we're supposed to take this, apply pi, and multiply. And I'm claiming that should be 0. And so far, all we know is that these are just some scalars. I mean, if sum ij is 0, that means one of these terms is a constant, but that doesn't mean that that constant is 0. It means it's a constant. Okay? But the key is pi, right? The key is pi because I claim that on degree 0, pi is 0. And so let me make the next observation. Let's analyze what this map does. Okay? Because this map is... So in other words, let me claim, and I'll prove it in a second, that pi of the things of degree 0 is 0. Anything of degree 0, pi sends it to 0. And if that's the case, that means that if I apply m to the n minus 1, pi tensor n, delta to the n minus 1 of hd, each one of these things has a term that has degree 0, and pi kills it. Okay? And so that means that each one of these tensors has one coordinate equal to 0, and therefore this is equal to 0, and this is equal to 0. Okay? So that means that if you plug in something of degree d into S, then you're going to have at most d terms here. You're not going to have more. So things are finite. Modulo this claim right here. Okay?
But in the case of something that has infinite degree, then does that summation will actually be infinite?
Nothing has infinite degree. So this we have h as a direct sum of h0, h1, but every term in every element of the Hopf algebra is a finite sum of things of finite degree. And so every particular element has some finite degree, and those degrees are unbounded, but no one thing can be of infinite degree. Okay, so I claim this, but then I need to understand what this pi is. Okay, so what is this pi doing? And so that was the next thing I was going to explain, which is the following. What about this pi? Let me remind you of what this diagram is, or maybe kind of budgeting my board here. So maybe I'm just going to go over here and write down the next observation here. So that was observation 1. Observation 2 is the following. A graded Bialgebra is connected let's say H is connected if and only if U epsilon restricted to degree 0 is equal to I restricted to degree 0. And in particular, if you are connected, then U epsilon is equal to I and pi is equal to 0. So why is this? So this will imply this. And why is this? Because we have the following thing. Remember that we have this commutative diagram from K to H to K, where this is the unit, and this is the co-unit, and this one is the canonical isomorphism. Okay? These things commute. So, look at what happens here. The point is this. The point is, you're going from here to here, and this has dimension 1, and this has maybe some bigger dimension, and it has dimension 1. Okay? So, if this is not connected, that means that this has dimension greater than 1, which means that these cannot be isomorphisms. Okay? And the identity on H0 is something that has, let me write it down. Okay? So if H0 is not K, so it's bigger than K, let's say if the dimension of H0 is bigger than 1, then what I'm saying is this, that U epsilon of H0, the biggest it can be is dimension 1, whereas the identity on H0, this is the identity, so this is the dimension of H0, which is bigger than 1. So these two things are not equal to each other. Okay? Whereas if H0 has dimension 1, then basically these are just going to be, U and epsilon are going to be inverse maps of each other. And so U epsilon is just going to be the identity. Okay? So if the dimension of H0 is equal to 1, then if you just restrict this to H0, you're going to get that U and epsilon are inverses of each other. And therefore, when you compose them, you get the identity. Okay. Now, what is this really doing? How should you think of this map pi? Let me summarize it better. The thing is, remember, everything here is graded, right? And so pi is going to take degree 0 and kill it. Now, what does pi do to the higher degrees? So if d is of degree 0, okay, so this guy has degree d. So if I take something of degree 0, then pi kills it. But if I take something of degree bigger than 0, then what happens? Pi is I of hd is just hd. And what is u epsilon of hd? Well, if you remember, my condition of graded said that epsilon kills all higher degrees. I said that epsilon of hd has to be 0. Okay? And so here I get hd minus u epsilon of hd, but that's 0. Okay? And so all this map pi does is that it kills your constant coefficient. It kills the degree 0 thing and keeps everything else. Okay? So pi is actually a fairly simple map when you think about it like this. So pi just removes the degree 0 part. Okay? This is the moral of the story here. Okay. So is that good? And so let's think again what this formula does. This formula just, S of an element just takes the coproduct and splits it into n things, kills the constant part of each one of them, and then multiplies them again. Okay. Now that we understand that formula, we can prove it. So let me prove this formula. What is mn minus 1 of pi tensor n of delta n minus 1 of h? We can do this in Swidler notation, right? So we're taking the n minus first coproduct, and so this gives me h1, h2 up to hn. I apply pi to each one of them, so I get pi of h1, tensor pi of h2, etc., and then I multiply those numbers. So it's just pi of h1 up to pi of hn multiplied. Okay. And again, here you see I'm sorry? I didn't put the signs yet, right? So I'm just considering this part. This is where you start saying sometimes Swidler notation is nicer than the other notation. In Swidler notation, this is easy. Now, what is this? Actually, if you remember, this is exactly convolution product. I mean, if I only had 2 terms, then it would be the convolution of h and h. Here I have n terms, and so it's just, sorry, it would be the convolution of pi and pi, and I have n terms, and so this is just the convolution of pi with itself n times. Okay. So S of h is just sum over n greater than or equal to 0 of minus 1 to the n minus 1 and pi, let me write it like this, pi convolution n. This is the nth product of pi with itself in convolution product. Okay. S is equal to this. Okay. Now I want to show this is the antipode, and so what I have to check is that S convolution I is the identity. So I need S convolution I should be the identity, right, which is u epsilon. So let's compute.
And then what happens after the any starting times?
From here to here?
Was that, yeah.
So,
Just letting S be that?
so S is equal to sum over n greater than or equal to 0 minus 1 to the n minus 1 and this stuff. And I just showed that this stuff is pi convolution product to the n. So this is S rewritten, and now I just have to compute S convolution I and hope that I get U epsilon. Okay? So let's compute S convolution I. So S is this. Convolution I. And what is I? Well, I'm going to write I as pi plus U epsilon. Okay? So what do I get? I get sum n greater than or equal to 0 minus 1 to the n minus 1 pi nth product times pi means, so I get pi to the n plus 1 plus sum n greater than or equal to 0 of minus 1 to the n minus 1 pi to the n convolution with U epsilon. But remember that U epsilon is the unit of convolution. And so it just goes away. Okay? And so what do I get here? Well, you see actually this is just the negative of this pretty much. Maybe it's going to be clearer if I put, let me change this minus 1 to the n minus 1 to minus 1 to the n plus 1. Okay? And so you see, what I have here is each convolution product with the same sign as it. And here I have each convolution product with the opposite sign. And so everything cancels except for which term? Which term? I don't know why I'm getting this backwards, because it seems that the only term that does not cancel is pi star 0. Right? But I don't know where I don't know why I have this minus sign. That's what I'm worried about. That minus sign shouldn't be there, so I made some mistake along the way. But what is pi star of 0? So pi star of 0 is should be U epsilon. Right. Sorry, say that again? Here?
So those are negative 1.
Uh-huh.
You're going to have delta negative 1 and negative 1. If you plug 0 into that. And negative 1 is u, delta negative 1 is v.
So you're saying that I should get pi.
So we do get the u thing. I never get the negative 1 from this. Because 0 pi to the star 0 means we have, going back to this definition of what pi star is, means n is 0. So we have n to the negative 1.
Uh-huh.
Then, what is that pi star? Well, whatever.
Yeah, okay. So I see what you're saying. So if I wanted to say what pi star of 0 is, I should use this definition, which is how I define this to be. And pi star of 0, it should be basically m minus 1 delta minus 1, which is u epsilon. So the u and the epsilon are okay, and I don't know where that minus sign is coming from, but it shouldn't be there. Maybe it's just this. Maybe the formula is this. Yeah, that's what it is. That's okay. Yeah, okay. Good.